Can we get a check? Check. Sounds. Test 1 2. Test 1 2. Good morning, everybody. How's the sound? All right, so here we are. Happy Wednesday. So last time we made the transition from ideal gases to real gases. We went into the realm of the real. Suddenly things got real. Maybe for some of you that happened Monday night on the midterm. But we're talking here about real gases and the onset of reality. So what we found was intermolecular forces caused the gases to condense into a condensed phase, into the liquid. And we saw that was due to attraction, and we were able to draw the potential energy for that attraction and correlate it with the energy in the gas per particle. And then we looked at the distribution of energies to see which fraction of the sample was below that energy at which temperatures. So we could decide when conditions were correct for the intermolecular potential to overcome the kinetic energy and cause the gases to condense. We looked at the origin of those intermolecular forces, and we decided that hydrogen bonding is the overall dominant force when it's available. So when you have hydrogens and dipolar molecules, or a charge around which the hydrogen can cause the water molecule to orient, that causes a strong interaction, and that's a strong potential energy, and it would take a lot of kinetic energy to overcome that. That led to very high boiling points for molecules where hydrogen bonding is important, especially water and hydrogen fluoride. We saw those anomalously high boiling points compared to other substances where hydrogen bonding isn't as important. And hydrogen bonding is one of the most important forces in biological chemistry, which a lot of you guys are interested in. Hydrogen bonding is one of the most significant forces that holds proteins and DNA in their native structures. So the macromolecular structures are stabilized to a great extent by hydrogen bonding within the molecule. So you may know that proteins are long strings of amino acids, but they don't exist in long strings in nature. They don't have a function until they fold into a macromolecular structure that's often very complex, but that structure determines how they function. And hydrogen bonding is a big part of that. So today we're going to continue and talk about the phases of matter. So we've seen where the liquid phase can form from the gas phase, but we can continue and look at the other condensed phase, and we group the condensed phases, solids and liquids, into one category. And in general, the transitions between the diffuse phase, the gas phase, and the solid and liquid phase are something that is a topic of interest for us, because the transitions, those phase changes, are vital to all of the processes these substances undergo, especially water on Earth. Certainly one of the most prevalent compounds on Earth, and how it functions determine how we function to a great extent. So what we're going to do is say, we've been looking at pressure and volume plots, and we were looking at pressure and volume plots, PV plots for ideal gases and real gases. And what we'll do here is look at pressure and temperature. Temperature we can immediately correlate to the energy of a gaseous system in a very straightforward way. The energy is 3/2 RT for a gaseous system that's an ideal gas. So, but we expect the other phases to exist. And if you think about high temperatures and low pressures, so this region of a plot, you'd expect to find gases at high temperatures and low pressure. So the bottom swath of PT space is where a gas would exist. Uh, if you increase the pressure or lower the temperature, you expect to find liquids, and further lowering the temperature and uh, increasing the pressure, so high pressures and low temperatures, you'd expect to find the solid phase. So overall, PT space has these gross distinctions: gases here, liquids here, solids here. We can divide them actually fairly precisely. So we can draw lines that separate the solid and the gas, and the liquid and the gas, and the liquid and the solid. So along these lines, very precisely, there's an equilibrium between the liquid and the gas, or the solid and the liquid, or the solid and the gas. So along the lines, both phases exist, and there's no preference for either one of them. There's a delicate energy and thermodynamic balance, and that balance is going to be the subject of a long conversation after this, where we see how equilibria stay in that delicate balance. There's a couple points of interest when the lines come together. For instance, here, that's the triple point, and the triple point is the point where the solid, liquid, and gas phase can all exist. So you have particles freely interchanging between the solid, liquid, and gas phase at the same time. So it's not observable generally in nature. The triple points of substances are generally at extreme conditions. So here's carbon dioxide phase diagram. The triple point is 5 atmospheres and minus 56 Celsius, so we don't normally see that. This point here is called the critical point, and it will correspond to a critical temperature. And we talked about that in detail last time. The critical temperature is the temperature that separates ideal and real behavior. So beyond the critical temperature, we found gases behaved ideally in that we did not have a phase transition. We didn't go from liquid to gas. We were able to compress them smoothly, and we had ideal gas behavior. P times V was a constant out in this region. And you can see that stops abruptly the liquid and gas phase separation. So there's no point beyond here where you have an equilibrium between two phases. Out here, single phase beyond the critical point. The critical point for carbon dioxide, not far from standard room temperature, but extremely high pressure, 73 atmospheres. So clearly these plots aren't to scale, and it's more obvious if we look at the condition for water. So here's water phase diagram, and the same general topology occurs. We've got gases and solids and liquids, and I've got a break here in the temperature scale. Water is an extreme substance. It's one of the most common substances on Earth. It's also one of the most unique. And we can do the same division of the phase diagram into the various phases with these precise separators where the phases are in equilibrium, and the triple point and critical point can be found. And for water, the triple point is very near the freezing point, just a few hundredths of a degree above 0 Celsius, and quite low pressure. So I've written the pressure in torr here. An atmosphere, 1 atmosphere is 760 torr. So this is down near very low pressure as well. The critical point for water, and you might expect, because water has these very strong intermolecular interactions, that this is going to be very extreme point. You have to go to very high temperatures to get water to behave ideally, to get water to stay in the single phase. Water, essentially, the condensed phase is stable. It has low energy because of those attractive forces. And we've seen when things come together, a plus and a minus comes together, that goes to low energy. And those intermolecular forces are large for water. So water overcomes the kinetic energy of gaseous particles and condenses into water liquid very readily, because that's a deep potential well. So you have to go to extreme conditions to overcome that. And those conditions are 650 Kelvin. So we're going to crazy high temperatures and remarkably extremely high pressures, 215 atmospheres. These are crazy high pressures. Those are the kind of pressures you're never going to encounter. If you have a compressed gas cylinder, you can get to pressures in this order of magnitude. And frequently, even in those compressed gas cylinders, you have less pressure than that. And those are incredibly thick-walled cylinders, round in shape, so they have no weak corners, and they can sustain and maintain those pressures without exploding. So water, crazy unique in that it has a extreme critical point, and just again emphasizes the fact that water is a very unusual substance. So we can look at the triple point and the condensation point for carbon dioxide, because those are not very extreme. And I didn't load those in advance, but let's see if I can get to them. I'll start them on the other machine. So we'll look at.
Heat up the carbon dioxide to its critical temperature.
So here we have liquid carbon dioxide. Liquid carbon dioxide, because we have it under relatively high pressure and relatively low temperature, but we could find this point on the phase diagram, and we could tell, is this point on the phase diagram in the liquid region? So here's liquid carbon dioxide. Now let's look at that that point. Oops. Let's. So that point where we were in the relatively high pressure, we were around 50 atmospheres there, and a temperature kind of just below room temperature, we were in a region here on the phase diagram. And we would predict under those conditions we'd have liquid carbon dioxide. If we change the pressure or temperature, we should be able to find a condition where we go beyond that. So if we have a keep increasing the pressure beyond the 73 atmospheres. So if we start at a region here and we increase the pressure, we can get into the region where we behave ideally. So let's just do that. Look at that video there.
And because the volume of the tank is constant, we can also build up the pressure. As the pressure and temperature reach the critical point, the distinction.
So you can see we're increasing the temperature and increasing the pressure at the same time. And when we do that, the increase in temperature and pressure are moving through pressure, temperature, space. And you can see what's happening to the carbon dioxide.
Between the liquid and gaseous carbon dioxide becomes less visible.
This is the liquid gas boundary. And look at that. If you keep going, that liquid gas phase boundary disappears. You get one phase, and it's kind of a crazy phase. It's relatively dense like a liquid, but it fills the entire container like a gas. So you could think of it as an extremely compressed gas that is dense enough to have liquid-like properties, but it has the gas-like property that expands to fill the container. So we can find the triple point of carbon dioxide. So let's look at how that was done. So we increased, you could see we started in the liquid phase and we increased the temperature and the pressure. So we had liquid visible. We increased the temperature out along the temperature axis and the pressure, and we got into a point here where the gas or the substance behaved ideally, a single phase. That's cool. It's always cool to see a triple point, a ideal point of a substance beyond its critical temperature, and we can achieve that with carbon dioxide because of the reasonable conditions for that. We can also just condense it. So we have Lonnie here in the lab. He's going to condense CO2. So he's going to start at relatively modest conditions. So modest conditions, carbon dioxide. So this is around room temperature. So he's going to start somewhere here in the phase diagram, a low pressure and a modest temperature. And then he's just going to increase the pressure and get the carbon dioxide to condense into the liquid phase. He's going to do that by just putting it in a cylinder and just pumping on it until we get the condensation. I'm going to turn off the audio on that. So you can see increasing the pressure, and there's liquid carbon dioxide decreasing the pressure. It boils. So increasing the pressure, there's the liquid forming. See if we can get a good shot of that. Do it one more time, Lonnie, so I can get a good shot of it. And there we get liquid and make it boil. There's the liquid and the gas for carbon dioxide. So we can see a phase transition, the gaseous carbon dioxide here at the top and liquid carbon dioxide at the bottom. If we pause there, not only the video, but we pause in temperature pressure space, where are we? So as we go up from our room temperature and room standard conditions, and we go up, if we have both the gas and the liquid existing at the same time, we're somewhere along this line of equilibrium between the gas and the liquid. These are the only places, these lines are the only places on the phase diagram where both phases can exist. So it turns out, this is amazing. The phase diagram for water is remarkable in that there are many, many forms of solid water. So this has a lot of equilibrium lines. Each of these lines here are phase boundaries, and they're phase boundaries between different forms of the solid. So ice crystallizes in different forms depending on pressure and temperature, and there's transitions between them. And there's a lot. There's something like 10 or 12 forms of solid ice. You may know that in the Inuit language, Eskimos, they have about 20 words for snow and ice because they experience all of them. And and if you're a skier, you probably have half a dozen words for the conditions of the slope and how the ice feels underneath. You're generally not you're generally not experiencing all of those phase transitions, but you're experiencing solid liquid phase transitions quite a bit when you're skiing. Um, this is a remarkable uh, phase diagram, and if you go to this website, it'll be on your pages for this lecture. This is an interactive diagram, and you can touch the various areas and see the forms of the water. We're not going to do that, but it is kind of fun in a geeky kind of way. Um, the website, heck, I'll show you. I'll just show you the website because it's almost unbelievable in its detail about what happens to water. I wonder if I have the link here to uh, to show you. That might be the link right there. Let's touch that. So here is that website. And you can see the phase diagram for water. Oh, that's the front page. Water structure and science. Where's the actual phase diagram? I didn't go right to it. So I won't go there and show you that exact phase diagram, but I encourage you to go see it. It seems like there would be a link right here on the page. Water is the most studied, like one other molecule. Are these things links? That's table of contents, explanations, uh, phase diagram, phase diagram of water. Phase diagrams. Let's see if we can find that one. There it is. So there's that phase diagram, and you can touch various regions and see what's going on here. Has all the densities of liquid water as it changes. It has the properties of ice and water on Earth and Mars. And if you touch the various regions, you can get explanations of each phase of liquid water. Uh, it's unbelievable the volume of information about water on that website. So we know that ice crystallizes in water crystallizes. It's interesting that one of the solid forms of water, the most common one under standard atmospheric conditions, is hexagonal in structure because of that strong hydrogen bonding in water. So you can see demonstrated here the water molecules, the oxygens in red and the hydrogens in white, and they are showing the hydrogen bonds in water solid, and they're so strong that they make the substance, they make liquid water, that ice structure, uh, less dense than you would expect. That is, they keep these open spaces in the water ice structure. The hexagonal nature of that is reflected in snowflakes. And they have a hexagonal structure. And you've probably heard that no two snowflakes are alike. And that's generally true in nature. If you go to this website, though, these guys have made two identical snowflakes. So all your general beliefs are being shattered here about water. So let's go back a second and look at that phase diagram for water, because there's another very interesting part that we've just touched on here, and that is the density of the solid can be greater than the liquid. In the liquid, the hydrogen bonds are jiggling around, and the water molecules can actually pack more tightly, come together more closely in the liquid than the solid. And that is a unique feature. There's very few, in fact, I don't know of any other substances, I forget, that the solid is less dense than the liquid. And you know that because you've put ice in a cup before with water. The ice, the solid, floats on the liquid. And we don't experience solids and liquids together very often. Water is the one we see. Water is unique. Every other substance, the solid sinks in the liquid. That's a unique property of water, and you can see it by this negative slope of the solid liquid interface. If you increase the pressure on most substances, you increase the pressure, and here we'll just start anywhere here, increase the pressure, we'd go from gas to liquid to solid. Water, you can go from gas to solid, keep increasing the pressure, and go back to the liquid. So at high pressure, the liquid is stabilized. You can press solid water and turn it back into liquid water. And of course, life on Earth is dependent on that. So hydrogen bonding in another way helps us because ice does float on liquid water. Think about it if it didn't. Lakes would freeze from the bottom up. So we never would have evolved. All life in lakes essentially would be destroyed in the winters. You can imagine evolution just getting going, and then dang it, freezing solid from the bottom of our little pools, our primordial pools, and wiping out all that progress. Evolution having to start over every spring. So let's move on here to a chem quiz. So we've looked at these lines, these pathways in our pressure temperature space. I've drawn one here, a line in the pressure temperature space. Can you translate that to pressure volume space. So Ryan will start the iClicker system. Think about that in your small groups and take a vote. I'll join a group and talk with you. Can you put me in a group? Okay, we're back all together. Ryan will be able to show us what you're thinking, so vote if you haven't so far. That doesn't look good. Oh, there it goes. So B is popular. A and C have some votes. I think I agree with the B's. And as always with chem quizzes, this is to stimulate you to think about this and talk about it with your group. You shouldn't be concerned or worried if you don't get the answer, or even if you don't understand it at first glance. This is all about thinking about what you're doing together in a group. This particular chem quiz, I'm actually surprised that there are so many B's and people are converting to B's after I said I agree with the B's. Going from pressure temperature space to pressure volume space is not a trivial thing the first time you look at it. So let me give you my thinking on that. Switch back to my machine. So what you might have realized is you started out as a gas here, and what happened was you started out somewhere in pressure temperature space, but in the gas. But what you could have noticed is you started out in the gas phase above the critical temperature. And what's true above the critical temperature? The gas will behave ideally. So you could have tossed out A right away. Pressure and temperature are not inversely, or pressure and volume are not inversely proportional there. This you could have recognized as an ideal gas plot. This as a real gas plot. And out here, we behave ideally beyond the critical temperature. So you can translate between pressure temperature and pressure volume by thinking about the properties of the substance on the phase diagram, what transitions it'll occur. We never cross a phase boundary line. Nowhere on this increasing pressure line will we ever have an equilibrium between two phases. We'll behave ideally, we'll be in that situation where we get a phase that looks very dense, but it's still filling the whole container, still behaving like a gas. I'll go through this one with you. So which of these lines, so here we have 3 lines in pressure, temperature, space, A, B, and C, which corresponds to condensing carbon dioxide? So condensing refers to, of course, the gas condensing into the liquid. So here you are at temperature and pressure where you're in the gas phase. You increase the pressure and you become a liquid. That's a condensation. Turns out condensation is a more general term than that. It does also refer to going from the gas to the solid. That's also a condensation. You're going to a condensed phase, the liquids and the solids. So here you're also starting in the gas phase at point A and increasing the pressure to go to the solid phase. Excuse me, you're decreasing the temperature to go to the solid phase. Here, you're increasing the pressure to go to the liquid phase. So it turns out both A and B are fine answers to this expression. Condensed phases are both the solid and the liquid. So here's another one where we're trying to determine what's going on. Vapor pressure. So vapor pressure is the equilibrium pressure between the liquid phase and the gas phase. So those are the pressures where things are in equilibrium. So which of these plots is a plot of the vapor pressure of water? This is the water phase diagram. So now I'm staying in pressure temperature space, but I'm thinking about the equilibrium between liquid and gas, the various pressures, the various vapor pressures of water at different temperatures. So think about that. I'll hop into a room and we'll chat. Did you get a quiz started? Okay, we're back together. I apologize. The original chem quiz you saw was the previous one, but we corrected that. Let's go to Ryan's screen and see what you're thinking. Did we lose PowerPoint altogether? It's that problem where we can't get it back. Well, let's look at the result of the poll. Look at the result of the poll. B, the most popular, and I agree with the B's. See if you can get your PowerPoint back, Ryan. We'll go back to my PowerPoint. I agree with the B's, and Lucy in my breakout room, she's just said it better than I could have said it. She said, well, if you need to have the vapor pressure, if you need to look at the various temperatures at which the liquid and the gas are in equilibrium, you have both phases, and you want to see how that pressure varies with temperature, that is that line. So that is exactly what you're looking for in the vapor pressure for water. You go to higher temperatures, you get a higher vapor pressure of water. You go at various points along that line. So here at room temperature, you have a low pressure, low vapor pressure of water. It's related to the humidity in the room. You go up higher in temperature, you'll get to the point where a higher pressure temperature, and you'd find the normal boiling point when the vapor pressure is 1 atmosphere in this system. Oh, I am on my source. So let's look at that more carefully. So I'm going to draw that plot again here. I'm going to start at the triple point and go up to the critical point, and I can draw the phase diagram, the pressure volume space at the critical temperature. I know what that looks like. The critical temperature and pressure and volume space is the point where you just start to see real behavior. You get that inflection in the pressure volume plot. Above that, we behave ideally. Below that, I get condensation. What about some other points? So here I am above the critical temperature at that orange line. I can go to pressure volume space there and say, well, that is going to behave like an ideal gas. We did that as a chem quiz. What if I go below the critical temperature? Now I'm at 100 degrees C, the normal boiling point. So do we know what pressure that corresponds to, what the vapor pressure is? Well, it better be 1 atmosphere, and the curve better look like a condensation occurred. And indeed, that's what happens. You over here, that will be pressure volume space at the vapor pressure, 1 atmosphere, for that temperature. And we can look at some other points along the line. So let's go down here. Colder temperature, room temperature, 25 C. 25 C, we expect again a condensation, and the liquid phase is more prevalent. The vapor pressure of water at room temperature, just a few hundredths of an atmosphere. And you can go down here. I'm going to go down to 5 C. And again, you have this very low vapor pressure of water. You don't expect to see a lot of gaseous water in equilibrium with the liquid phase. So if you applied just a tiny pressure, this would go back to fully liquid phase. Just 9,000ths of an atmosphere more pressure, it would all be liquid. A little bit less pressure, and it stays in the gas phase. So that is how I correlate pressure and volume with pressure and temperature for the vapor pressure. So what's happening here? I'm going to put 20 grams of water in an evacuated flask and seal it at 25 degrees C. The volume of the flask is around 20 liters. What happens? I'll talk this one through with you. So if I put that liquid in there, 25 degrees C, where am I at the phase diagram? I have liquid, I'm at 25 degrees C. What I expect is to form some gas, and about 3 hundredths of an atmosphere worth of gas. There's no gas at all to start with. But I know that the vapor pressure for water at 25 degrees C is that 3 hundredths of an atmosphere. So another way to think of vapor pressure is the pressure of the liquid, excuse me, the pressure of the gas above the liquid at that temperature. And it turns out it doesn't matter if there was air in the flask or not. Water would get to this partial pressure of 0.03 atmospheres. Remember, gases behave like no other gases are there. So the water molecules evaporate and get to a partial pressure of 3 hundredths of an atmosphere, regardless of whether it's a vacuum there or not. So the vapor pressure at 25 degrees C, I know that. So that's the pressure in the flask, the total pressure in the flask, because I started with an empty flask. So 22 liters at 25 degrees C, 1 atmosphere of pressure, I'd have a mole of gas, but I'm at 0.03 atmospheres, so I have much less than a mole of gas. But I had about a mole of liquid to start with, 20 grams. Much less than that will evaporate. So you'll have a mixture of the gas and the liquid in that flask. So this explains largely the weather. Oops, the animations are broken here, it looks like. But this explains what happens in the atmosphere. So if you look at the various partial pressures, the vapor pressures for water, at 25 degrees C, the vapor pressure for water is 0.31. That's our baseline. If that is the case, the air is saturated with water. It can't get any more water in it than the vapor pressure. You have to put some heat in or boil it to get it to change from there. So that's saturated water, and you might see the gaseous phase if the conditions are right, because you might see fog at those conditions when you're there. We actually call that 100% humidity, when the air contains the maximum amount of the maximum partial pressure of water for that temperature. So here's 25 degrees C at 30% humidity. I've gone up in temperature, so now this is the vapor pressure. Or this is the actual vapor pressure in the system. I'm just telling you that's what it is. The vapor pressure I could get to is 0.03, so I'm less than 100% humidity. So I don't see any of the gas, the vaporous, cloudy water. If I continue to go up in the atmosphere, so though that mass of gas rises through the atmosphere, that mass of gas is carrying water with it, 30% humidity, it's carrying that water with it, and as gases raise in the atmosphere, they cool. It's called adiabatic cooling. We're going to talk about that in a few minutes. So it cools. Well, if this cools from 25 to 5 degrees, then that vapor pressure that pressure of partial pressure of gas that was there becomes equal to the vapor pressure, and you get back to 100% humidity, and you can see the vapor for water, and that's where you get your clouds. So that explains cloud formation in the atmosphere. I should have brought a slide along. I was watching the weather, uh, a weather personality on television. Uh, he explained this completely wrong, and I was so incensed. I took I had my phone. Thank goodness I took a picture of the screen, um, and so a meteorologist, someone who is supposedly trained in um, the properties of the atmosphere, got this wrong. You guys would be able to explain that to him. So you can see this cloud formation. I'll show you a video here of that happening. Oh, poop, it's a sponsored video. So there's an ad. Stand by. Lonnie does this, but um, uh, I couldn't find Lonnie's uh, picture. So what we have here is a tiny bit of moisture in that flask, and we're going to go to very high pressure, pump it up hard. So he's going to pump that with this hand pump. Oh, we already did it. He pumped it up with a hand pump to high pressure and then released the pressure suddenly. And when he released the pressure suddenly, that's the same as that gas going up through the atmosphere, lower pressure at higher altitudes. Happens very fast, so you instantly form a cloud in that flask. That's a really cool example of that. So here he is again. Oh my goodness sakes. Okay, it's going to run from the beginning. Oh, that's the next person who's going to make a cloud for us. I like the other guy better. Oh, but we got to watch the ad again. Okay, screw it. We'll go back to our PowerPoint. That video is linked, of course, in your materials, and you'll be able to play it yourself. That guy's actually pretty good. Not Lonnie good, but he's pretty good. So there we go. Now we're going to go from those gases to start explaining why those pressure volume relationships caused condensation, caused temperatures to drop, and dramatic changes in pressures causing those different phenomena. And we've already looked at it a little bit. We started out in this class with the first law of thermodynamics because we wanted to understand how energy interacts and how systems and surroundings energy flows between them. So we're going to go back to that. So a little bit of this is a review. The first law of thermodynamics we wrote down earlier, that if a system changes in energy, it has to be the result of heat and work, Q and W. Q for heat, W for work. And heat can leave a system or enter a system from the surroundings. When it leaves the system, we call that exothermic, and we get a negative sign. When it enters the system, we call it endothermic, entering the system, and we give that heat a positive sign. And we should remember that heat itself, the quantity, even energy itself, does not have a sign associated with it. There's no such thing as positive heat and negative heat or negative energy. Those are changes that have the sign. The quantities are magnitudes. The sign just tells you the direction of the flow, the change in a system or the surroundings. So there's work entering the system. I'm doing work on the system. I could be lifting it. I could be squeezing it. I'm putting some energy in the form of work. If I put energy in the form of work, that raises the energy of the system. That's why I have a plus sign there. Work done on the system is positive. It tends to raise the energy of the system. It makes delta E positive. And the system could do work. And if you do work, your energy goes down. So delta E is negative. You lose some energy. Delta E is the final state minus the initial state. So if your final state's bigger than your initial, you've gone up in energy, delta E will be positive. If you went down in energy, then your initial state, we can draw that. So the energy differences I'm talking about are, here's a plot of energy going up on the board. If this is my initial state and this is my final state, then this is delta E. And here the initial is bigger than the final. So final minus initial is negative. The final is smaller than the initial. That negative sign is a drop in energy. Delta E, in this case, negative, less than 0. So that could have been the system doing work or releasing heat. So work and heat are how energy is moved around. Work and heat are not themselves state functions. They're not, you can't calculate them from the parameters in the system, the temperature and the volume. And you can't calculate a heat or a work. You can calculate an energy. And if there's an energy change, you can deduce whether work or heat occurred. So you work backwards from energy changes to heat and work. Sometimes you can measure the heat. You can have heat leave the system and go somewhere else and change the surroundings temperature and see how much heat was lost or gained by the system. In general, here's another statement of the first law of thermodynamics. The energy of the universe is always the energy change in the system and the energy change in the surroundings, and the change of the universe energy is always 0. So the amount of energy we had in the universe at the Big Bang, that same amount of energy is in the universe now. So that's a very profound statement, that incredible, huge Big Bang is now, that energy is the same in the universe. That gives you an idea of the magnitude of the Big Bang. That encompassed all the energy in the universe in a single point. And now the universe, you know the size of it and the amount of mass in it, the number of systems, all that energy came from the same point. So we think. That's what modern physics tells us. So let's look at work and energy and how that transfer of energy happens. So we did a little of this before, but work is, pardon me, work is force times distance. And you don't have to worry about too much about this physics, but if I change a height, I'm doing work over a distance. So if I change the height of this piston, I change that. What we're interested in is that also corresponds to a change in volume. If I change that height, I change the volume of the gas. If I change the volume of the gas, there's a delta V. We can relate the force to the pressure. So the pressure I exert times the change in volume is the work done on the system. And I say, we'll give that a negative sign. We give it a negative sign because if delta V is positive, that's an expansion, and the work has to be negative. So that's kind of an artificial sign. We just throw it in there to keep our conventions correct. We know the energy of the system, if it's a gas per mole, is 3/2 RT. So we can look at these changes. If delta V is positive, then the work is negative. If you expand, the system is doing work, so its internal energy must go down, its volume goes up. Is there a question?
Yes, there's a little bit of confusion on what a state function is.
So the question is, what is a state function? And that's an important distinction. Energy is a state function, work and heat are not. As you remember from the second day of class, a state function, two things. It can be calculated from the state variables of the system. So you can calculate a state function from the state it is in, from its pressure, its temperature, its volume. E is a state function. I can calculate it from its state. The temperature of the system gives me the state of the system. So a state function depends only on the state of the system. We can calculate any change in a state function. This is super important. Any change in the system from the initial conditions, because we can calculate the state there, minus the final conditions. Delta is initial minus final, so delta E. And that's incredibly important because it's often hard to track work and heat, but delta E is dependent on just the initial and the final conditions and nothing in between. It doesn't matter how you got from the initial to the final state. And you remember the second day I said it's like a blinder function. State functions are blinders. You look at the state, put on the blinders, open them again, and the system has changed, but you didn't see how it changed, but you know you can calculate that energy change from the new state, the new final state. And we said also, state functions was a little bit of a highfalutin name, like state functions, like the governmental positions. An equation of state, uh, it's not like equations of state travel with a motorcade and have parades accompanying them. They're equations of state, not people of state. We're talking about the conditions, not the governmental state. I can also compress a gas. If I compress a gas, delta V is negative, and therefore the work has to be positive because of that sign. Notice there's an equal sign if I expand. Work can be less than or equal to 0. Because when I expand, I could expand against 0 pressure. So if the external pressure is 0, then I can change my volume for free. We kind of saw this in the condensation. We're able to get a free compression because we changed the amount of particles in the system. So let's look at if we keep one of the things constant, the volume or the pressure. If we keep the volume constant, then the work has to be 0 because for our gases, the volume has to change, P delta V, to get work. That means all of the heat, all of the interchange, all of the energy change came from a heat flow. So I'm going to say Q sub V, the constant volume heat. That's just saying what conditions did this heat flow under? Conditions of constant volume. So the energy change is directly proportional to the temperature change. And that's always the case for an ideal gas. We know the temperature determines the energy, period. Energy is 3/2 RT for a mole of gas. What if I keep the pressure constant? I do something interesting here under constant pressure. I define a new state function. We're going to call that new state function enthalpy. And I'm going to call it the sum of these state functions. If you add up state functions, you always get another state function. So the pressure and the volume, those are obvious state functions, right? If you say I have a balloon at a certain pressure and I close my blinders and squeeze it together and open it again, I see a different pressure. That's an equation of state. It doesn't matter if it expanded and then contracted or uh, any other thing happened, temperature changed, all that stuff. The pressure and the change in pressure can be calculated from the final pressure minus the initial pressure. Temperature, final temperature minus initial temperature is the temperature change, regardless of what happened in between. So pressure, volume, energy, all equations of state. So, and this is just arbitrary. There's no, there is a deep, there's no deep meaning to it. We do this out of convenience, it turns out. Because if we do, then the heat evolved at constant pressure is the change in this function. This state function is the constant pressure heat. I won't go through all the mathematics to get there. All I'm going to tell you is this delta H is very similar to delta E. So we're going to use them almost interchangeably, and especially at constant pressure. And we operate at constant pressure very often. Life happens at constant pressure. So it's handy to have a state function that's exactly equal to something we can measure. The constant pressure heat evolved. So in this case, this special case, when heat is evolved at constant pressure, that causes a direct change in a state function. So that's why we do it. And under constant pressure, delta H is proportional to delta T. So this enthalpy thing just comes in because it's convenient to work at constant pressure, and we can measure heats going in and out of a system by constant pressure and correlate that directly to a state function. So let me just ask you then. An ideal gas expands isothermally, that's without changing its temperature. And it turns out it could have changed the temperature in between, but the initial and final temperature are the same. That's what a state function is. However, assume that the temperature didn't change through any of the process. You don't have to, but let's just assume that's true. And it expands against a vacuum, zero pressure. What is Q? And all I'm asking is the magnitude of Q. Bigger than zero, equal to zero, or less than zero. So think about that for a second, and we'll take a vote. We ready to start? Okay. Your chem quiz has captured this slide, so I'll show you. Oh, poo. I was going to try to show you the group of four. I will have to do it slightly differently here. Come on. The group of four is back there. Oh, it's slightly out of order. Okay, you guys can look at this. That's the information you need to do to use your chem quiz. Talk about that, and we'll come back and look at the answer. Okay, we already have 80 votes or so, so that's a lot of you. Let's see what you're thinking. Spread out. There's no real consensus anywhere there. So let me give you my thinking on this. So we kind of had the information we need here on the board. What is going on? Well, it's the process. Oh, I zipped forward. Stand by. I zipped forward in the presentation, so I have to go back to that chem quiz, which I think is that one. Yep. So we had an expansion at against a vacuum. So an expansion against a vacuum, I'm expanding, and if I expand against a pressure, I would have to do work. If I expand against no pressure, I'm the system and I push, but nothing is pushing back, I don't have to do any work. I didn't ask you about the work, I asked you about the heat, but something else crucial happened, and it's an ideal gas. The temperature is constant, same temperature. So if the temperature changed, did the energy change? No. If you take nothing else home from Chem 1A, take home the fact that the energy and temperature of an ideal gas are locked together. The temperature defines the energy exactly. The energy is only a function of the temperature. If the temperature didn't change, isothermal, then the energy didn't change. So I can say it's isothermal, so the energy didn't change. And that means the work has to be equal to the heat in magnitude, opposite sign, because energy is work plus heat. But the system didn't do any work because it expanded against a vacuum. So no flow of heat. So that's a fundamental thing. Isothermal processes, we'll talk about them all the time. In general, isothermal processes take time to proceed, because to stay isothermal, the system to stay the same temperature, it often has to give off or absorb heat to stay at the same temperature, because it needs to stay at the same energy. So it has to absorb heat if it's doing work. And heat flow is slow. So isothermal processes, you often have to do painfully slowly, or do it and then wait a long time for the heat to flow back in to get back to the same temperature. Because those are state functions. You could have done it slow and stayed the same temperature the whole time. Initial minus final, delta T would be 0. Or do it fast, but then wait until all the heat flows and get to the same temperature. Delta T still 0. Delta E still 0. Heat did flow, yet energy didn't change, and I can calculate it from the heat, the temperature change exactly. So now I'm going to compress it, ideally, the ideal gas, isothermally. So I'm going to squeeze it, and then wait until the temperature is the same, if it changed at all. And then I know it was isothermal. It's not isothermal in this case because it was the same temperature for the whole process. It's isothermal because temperature is a state function. Final minus initial is isothermal regardless of how I got there. So an ideal gas, isothermally compressed, what is Q? Well, I compressed it. So if I compress a gas isothermally, now this still all is true. The energy cannot change because the temperature did not change. Maybe it changed in between on the process, but the temperature change is uh, is final minus initial. So I could do it very slowly or quickly. As long as delta T is 0, delta E is 0. But in this case, I did work on the system. I squeezed it. The only way to get that gas to compress is to force it to compress. I had to do work as the surroundings. I had to do work on the system. If I do work on the system, the work is positive, so the heat has to be negative. What does that mean? I did work, so doing work, positive work, that's going to raise the energy. But it's isothermal. If I raise the energy, the temperature would have to go up. So what do I have to do to keep the temperature constant? Take that energy that came in as work and bleed it out as heat. That's what this says. Any work you do has to be compensated. Work done on the system has to be compensated by heat leaving the system. So, summarize. Isothermal contraction and expansion. If I expand, the system does work, so that's negative work. And heat can flow in to keep it isothermal. If heat flows in, that would raise the internal energy. If I compress, then I do work on the system to stay isothermal. Every joule of work has to be bled out as a joule of heat. Same thing when I expand it. If I put a joule of heat in to get it to expand, I have to let it do a joule of work to keep the energy change 0. And if energy change is 0, the temperature change is 0 for an ideal gas. There's another set of conditions, and this one always causes humongous consternation. And this is that adiabatic process that I talked about in the atmosphere. Adiabatic processes are just processes where heat doesn't flow. Essentially, it's easy because you get to set Q to 0. So, and essentially adiabatic processes are just ones that happen fast. If something happens fast, heat does not have time to flow. Work you can do fast. Heat takes time to flow. So the reason we talk about it is a lot of processes are fast. So it's a common process. We give it this horrible name, adiabatic, but just cross that out and say fast expansion or contraction. Under fast expansion or contraction, Q, there's just not enough time for it to flow. So Q is 0, but you can do work. So work can be positive or negative. And it's equal to the energy change of the system because that heat is 0. So there was an adiabatic expansion, happened super fast. It expanded against a constant pressure, so it had to do some work. And you say, well, what is the sign of that work? It's less than or equal to 0. You can always remember, if I do work, that takes some of my energy to do that work. So I have to lose energy. So there must be a negative sign to the work. Negative sign to the work makes delta E tend to be negative. So I used some of my energy. I used it to do work. If I compress the system, then I do work on the system. That tends to raise the energy. And of course, there's that equal sign in the expansion case. That equal sign is for if I expand against 0 external pressure. I think we'll just stop here. What's today, Wednesday? We'll stop here. We'll pick up with this chem quiz on tomorrow, because this is kind of a fun one. We talk about it for a little bit, and we can watch some demos. And we're near the end of our time, and I am about to completely lose my voice. So I know I sounded less enthusiastic than usual today. I'm literally trying to keep the tone of my voice constant and the volume constant to preserve it. So I apologize if I wasn't as animated. Hopefully over the weekend I can recover. I'll see you tomorrow. Same bat time, same bat channel. Take care, guys.